So let's look at this. We've got a second order differential equation to solve, second order. The right hand side is 0, so it's homogeneous, if you remember the terms we were looking at last week. And we're given some initial conditions. When x equals 0, y equals 3 and dy by dx equals 7. What's the first step? Good. Let m equals differential. Form what's called the auxiliary equation. And then solve. So I'll just pause this while you solve that quadratic equation using the quadratic formula, which is this, if you can't remember. All over 2a. Hopefully you're going to end up with something like that. We can find the square root of 16, but this, of course, is the thing, isn't it? This is negative. We've got negative roots. So we're in the position where we've got to introduce the complex number idea. The imaginary number j, which is the square root of -1. So now we end up with m equals, if I separate these two out, -6 over 2 plus or minus the square root of 16 over 2j, where j is the square root of -1. And if you remember back to our work on complex numbers, at this point we separate out the real and the imaginary parts. So n turns out to be -3 plus or minus square root of 16 is 4 divided by 2 is 2j. So we get that as our solution. So now look at the table of roots. Here's mine. We've got a root of this form, look. Alpha plus or minus beta j. So alpha is -3 and beta is 2. So in our particular one we can now write down the solution. So y equals alpha equals -3 and beta is 2, so we can now write our general solution. Y equals e to the alpha x and then we've got a trigonometric term inside. We've got a cos beta x plus b sine beta x. And beta is 2. And that's our general solution. -3, of course, because alpha is -3, so here's a -3. If you look back at these solutions, you can see that alpha is -3, so if we go back to your table, if you've got a complex solution, alpha is the real part, and beta is the number inside the imaginary bit. So beta is whatever that number is, which is 2. Not 2j, just the 2. So that's why alpha turns out to be -3 and beta turns out to be 2. By the way, that is not a j. It's a colon. Not a colon, not even a colon, it's a semicolon, yeah. So that's our general solution. We've got to find our constants now, a and b. So to get the particular solution we have to form two equations, two simultaneous equations, because we've got two unknowns, a and b. And if we look back at the problem, we've got the ability to set up to, because when we know that when x equals 0, y equals 3, and the differential is 7, so we can form 2. The first one, we just put these conditions into the original equation. When x equals 0, y equals 3, so in here, when x equals 0, y equals 3, so I can, and then work out get one equation. But then what I'll need to do is differentiate this side. And then I can write that the differential equals 7 when x equals 0. How do I differentiate this right-hand side? What rule have I got to use, Lewis? No. What rule, before I even think about differentiating? I'm differentiating with respect to x, so x appears more than once. No. I've got one function involving x here, multiplied by another function involving x. No. The product rule, because I've got one function multiplied by another. Sorry, Anna, did you say? Well, we can't, because they're not added. They're multiplied. If they were two added, we could do each one separately. But yeah, so we've got to use the product rule. So I'll pause this video. You put in the initial conditions when x equals 0, y equals 3, and then I want to differentiate the right-hand side using the product rule. And then when x equals 0 again, the differential equals 7. So you come up with two equations, and hopefully you can then find A and B. In fact, I'll stop this video here, and then the next video will go through this particular solution.